Hi Year 12. Today we're studying our new chapter. It's chapter 6, it's trig functions, and we're going to start with 6a. We're going to have a look at the behaviour of sin x near the origin, a little bit of tan x, and see what happens with cos x as well. So we know these graphs from year 11, and you should hopefully remember what they look like, but if not, you can jump onto GeoGebra or Desmos and just graph y equals tan x, y equals cos x, and y equals sin x. Just quickly plotted them for you. My graph here though is looking at radians on the axis there, so we need to remember how to convert between radians and degrees, and I'll have a look at that in a moment in the video. So it's going through 3.14, which is pi, which is 180 degrees. So that's sine. So sine starts at 0 and it cycles either way around, and it differs by cos. Pop cos in there as well. We can shift sine to become cos. Okay. And our tan, and cos is starting at 1 on the y-axis. Tan, totally different. Tan looks like that, and we have asymptotes as we move through. Okay, so we're not actually looking at that in this chapter at this point, but you may need to, if you don't remember that, to go back and have a little look at that from our trig chapter last year. What I want to talk about here is the behaviour of sine and tan near the origin. So if you have a look at the diagram down here, there's a, hard to see, but sin x curve there that curves over to the right, and there's a tan x curve that curves upwards and down. So in the middle of those, we've got the line y equals x, and what you'll notice, as x is really tiny, or x is near the origin, both of those curves, y equals tan x and y equals sin x, are behaving exactly the same way as the line y equals x, which is something that we can use. So it says the line y equals x is a tangent to both y equals sin x and y equals tan x at the origin. When x equals 0, the derivative of both sin x and tan x is 1. And that would be the same as the derivative of y equals x. So what we can actually gain from that is that as x goes to 0, sin x over x is equal to 1. As x goes to 0, tan x over x becomes closer to 1. I think a better way to think about this is in this little box down below, looking at the small approximation. So if we work in radians, so popping our calculator in radians or converting our degrees to radians, if our angle is small, and suppose that x is small and we're written in radians, then we can actually show that, or use the approximation, that sin x is approximately equal to x, and that cos x is going to be approximately equal to 1, and that tan x is going to be approximately equal to x, but only when x is small and x is in radians. So I might just highlight those for us. So when x is small and x is in radians. Now, if we have a look below, we're going to have a look at the example, and that's probably a really good example that shows us how that actually works. Okay, so the first example here says, use the small angular formula to find approximations for the following. So we have a small angle here after sine. We've got 1 degree, and that, if you think of how big 1 degree is, if you were to draw that, that's quite tiny, so it's a small angle. And we want to find an approximation for sine of 1. So we know this, that sine of x is approximately equal to x when x is small and when x is in radians. So I'm going to change x here, our 1, to radians. So our formula that we used last year, and I think I've dropped it over here, we go. A little bit messy, but it's saying if I want to move from degrees to radians, I'm timesing by pi over 180. If I want to move from radians to degrees, I'm timesing by 180. Over pi. And the thing that we would want into times or change into is our top line. So the radians are in terms of pi, it's the top. Our degrees are not in terms of pi, so pi is not at the top. So what I've done here is just changed my 1 degree to radians. So I've times by pi over 180. If I pop that in my calculator, I get 0.01745. That's a handy approximation to use, but if we were to actually grab our calculators out and pop our actual sine of 1 degree in, so not radians anymore, we should get pretty much the same number. So if I go sine of 1, and you can see my calculator there's in degrees, I'm going to get a value, 0.1745, which is very similar to what I've got there. So therefore you can see that, yes, it is a good approximation. So doing the same with cos is slightly different. The approximation for cos is saying that if cos of x and we are in radians, it is going to be approximately equal to 1. So that's a nice easy one. So we've got 1 there. Third one, the tan. Tan and 1 degree. So tan and 1 degree is going to be approximately equal to that value of x if it's in radians. So I need to change that 1 degree to radians, like I did with the sine, times it by pi over 180. I get 0.1745. And again, you can look at your calculator, and if you pop tan of 1 in, you're going to end up with pretty much a value that's the same that you have there. So that's a handy way to use those, and you might find we need them, we may not. But at this point, let's try and use this in an example. So the example says the sun subtends an angle of 0 degrees, 31 minutes at the Earth. And there's a diagram over here to explain what that's doing. And it is 150,000 kilometers away at that subtended angle. So this angle line here is 150 million kilometers. We want to figure out what the sun's diameter is. Okay, so we know the diameter is twice the radius, so I've marked in 2 radiuses. I've split up the center, which we can do, because when we're subtending these angles, we're assuming that both of these, well, not assuming, we know that the angle that's subtended on the top and the bottom are going to be the same, so the sides are the same. So the theta is 0 degrees, 31 minutes. Now, I'm going to do this 2 ways. I'm going to do this to start with in terms of using sine and just right angle triangles. So if I have sine of theta, I actually want my theta that I want to use in that triangle to be half of this angle here, half of 0 degrees, 31 minutes. And that would be, and I haven't written it in there, but half of that would be 0 degrees, 15 minutes, 30 seconds. So using my right angle triangles, I've got a right angle down here, I've got an opposite being r and hypotenuse being 150 million. So sine of 15 minutes, 30 seconds is equal to r on 150 million. Rearranging that, basically timesing both sides by 150 million, will get me an r that is equating to this value. I want a diameter, so I've doubled it. It's not a pretty looking value. What we normally do when we're working in numbers that are really large or really small, we're going to have a look at scientific notation. So what I've done is looked at about the first 3 digits and rounded to 3 significant figures and times that by 10 to the power 6. So that's my diameter of the Earth, approximately. Okay, we can do it that way. However, because we're working at such small angles, like here, 0 degrees, 31 minutes, I can use my approximation to work out this as well. So what I've done is change that degrees, 0 degree, 31 minutes, to radians. So what I've done, but there's a little trick in here, ours looks at degrees to radians. So I need to think, well, 0 degrees, 31 minutes, that's 0 degrees. It's going to give me a 0 answer for radians, but no, 0 degrees, 31 minutes is 31/60th of a degree. So that's the fraction we have of the degree. When I times that by my radian conversion, pi on 180, I end up with 31 pi over 10,080. Now that's my whole angle. I chose to use my whole angle to do that because I didn't have to deal with the minutes and the seconds, only the minutes. So what I've then done is halved this radian answer to get me the angle that's I need to deal with, which is just half that top angle in there. So what I've done is got my 31 pi over 10,800 times by half or divided by 2, and this is what I've ended up with in radians as my theta, 31 pi over 26,600. Okay, now let's think what that means. Okay, it's moving across. Now since theta is tiny, okay, and we've got a very tiny angle up there, sine of that angle is going to approximate theta itself. So using the same formula as before, sine of theta is opposite on hypotenuse. I've replaced my sine of theta with just my theta. So I'm saying theta is equal to opposite on hypotenuse. So my radius is going to be equal to my value for theta, which I put in radians over here as 31 pi over 21,600 multiplied by 150 million. And I get a radius equal to this. I've doubled it to get my diameter, and I've written it the same way in scientific notation. And what you'll notice, if I zoom out in here, that my 2 values are nearly identical. So we have got a really good approximation to the diameter of the Earth without having to do too much trig calculations and just used our approximation. So that's one way that we can use small angles. Noting scientific notation is a lot easier to read and understand, and that should be in kilometers, guys. I'm just going to pop kilometers in both of those.